So in the last video we missed out some point there. This is what we are having. It was not recorded properly. There was a sudden drop in the recording. So here the time period of the triangular waveform, what we are seeing from the VCO is at twice the delta t. So we know that delta t, delta t is nothing but what? It is a 0.25 VCC into CT by I. Just substitute that value, you will come across 1 by t equals to the 1 by 2 delta t equals to the I by 0.5 VCC into CT. So F naught is nothing but the reciprocal of the time period. So the time period is nothing but twice the delta t, and this is what we are having. But we know the I value, right? I value is nothing but what, man? It is the current passing through this particular terminal. Okay. So current passing through this one is nothing but current passing through the RT is nothing but what? It is a voltage potential. Sorry, that is the voltage drop across the RT by RT. So voltage drop across RT by RT. So that is nothing but I'm having this one, right? What is that? Go back for I value, right? I. So I is nothing but it is a current passing through the RT resistor, which is a VCC minus VC by RT, which is a VCC minus VC by RT. So substitute this value in the equation number 2, then you will get the equation number 3 like this. So finally, F naught equals to 2 into VCC minus VC by CTRT into VCC. CTRT into VCC. So this is a F naught value. This is a F naught value. So based on this particular what is that diagram? Sorry, based on this particular equation, we can comment that the F naught is depending on the three parameters now. Three parameters. Okay, now so, three variables on the VC, CT as well as RT. We can't change the VCC, which is a power supply applied to the what is that VCO or IC. So CT is nothing but the timing capacitor, means by changing the timing capacitor or by changing the RT value, that is the timing resistor, or by changing the modulating input voltage which we are applying to the VCO to change the oscillations of our signal. By changing any one of these three components, that is these three variables, we can change the frequency of the oscillating signal. Okay, now we can change the frequency of the VCO. We can change the frequency of the VCO. But if you see the diagram, these CTRT are the physically connected. These CTRT values are physically connected to the VCC. Okay, now, to the VCC. Whenever you want to change the F naught value, you can't change the RT-CT value every time. You can, but you can change the VC value. You can change the VC value. So the frequency signal, this particular equation F naught is purely depends on the change in the modulating voltage. If at all there is a change in the modulating voltage, then F naught will change. F naught will change. So based on that, I can say that the VCO, that is a voltage controlled oscillator frequency, voltage controlled oscillator is changing the frequency of the uh, output waveform based on the input signal, so that is the conclusion of our VCO, voltage control oscillator. But in order to calculate, I would like to calculate one term over here, because F naught, here if you see this particular equation, whatever the equation we have over here, in order to reduce this one to a particular one, to a particular small equation, what I'm doing is I'm fixing the VC to the 7 by 8 times the VCC. What I mean to say that, here, if the voltage at the pin 5 is fixed, that is biased to the 7 by 8 times the VCC, substitute this value in place of the VC, then you will get the F naught equation, as a 0.25 by RTCT. If you are fixing the VC value, if you are not fixing the VC value, then if you are fixing the VC value, then F naught is depends on the RT and the CT. But if you are not fixing the VC value, then the F naught purely depends on the RT or CT or the VCC, VC. But as we know that we can't change the RT CT every time, but we can change the VC value, which is the modulating input voltage. Okay. Finally, we are supposed to define one factor in VC, voltage control oscillator case. Whenever we are taking the voltage control oscillator, we are supposed to define one factor called as a voltage to frequency conversion factor, which is indicated with the kV. It is nothing but It is a ratio between the output signal frequency by input modulating signal. Okay, now whenever there is a change in the output signal frequency, because of there is a change in the input signal voltage, if we take the ratio between these two, it is called as a voltage to frequency conversion factor. So this is the conclusion of your what is that, PLL, phase locked loop. It is a conclusion of your PLL. So I hope you realize the concept. Okay, I hope you realize the concept. So PLL is nothing but the phase lock loop. Phase lock loop is nothing but it is this particular PLL is especially used in the frequency demodulation, demodulation, and the phase shift, frequency shift keying, and also some other frequency components tracking parameters we are using the PLL. So PLL will enter into the lock stage whenever there is a whenever the input signal frequency and the F0 frequency both are equal, then the PLL will enter into the lock stage. PLL will enter into the lock stage. If at all the F0 value, we are supposed to define one more thing. If at all the Fs value is very far away from the F0, is very far away from the F0, as we know that error signal is generated in the two frequency components na, Fs plus F0, Fs minus F0. If these two are far away, Fs plus F0 is more value, highest value, that means it is a very large value. Fs minus F0 is also the a little bit large value, but that particular Fs minus F0 will not pass through this particular low pass filter. So means if the Fs is very far away from the F0, then I can say that the PLL is not in the means it is not in the tracking range, or it is not track the any changes in the input signal, or simply I can say that PLL is in the ideal mode. It is not doing its work. It is not doing its work because the whatever the input signal frequency we have, it is in the out of range, out of capture range. Whatever the input signal we are having, it is in the out of capture range. So at that time the PLL will sit calmly. I can say that the PLL is in the ideal mode. It is not turned on its operation. Okay, so this is all about your PLL. If you are having any queries regarding the PLL, let me know in the group. So actually when I was recording this particular topic, there was a problem, so I just made one more video. So if you are having any queries regarding the PLL, let me know in the group. Thank you.